as an example, let's try to determine the deflection and the rotation of this beam, given that this load is 100 kips, and we know the Young's modulus and the second moment of inertia. So, for doing this, we're going to want to use our equations previously determined, which is to say that the shear is going to be equal to the integral of the distributed load, though we don't have a distributed load in this occasion. The moment is going to be integral of the shear. That's a function of x as well. The rotation is going to be equal to 1 over the second moment of inertia, and the Young's modulus of the integral of the moment, and the deflection itself is going to be equal to the integral of the rotation. Or we could say 1 over the Young's modulus and the second moment of inertia times twice the integral, two integrals. Of the moment equation. So, when performing these sorts of problems, we're initially going to just start the same way that we did when finding our shear and bending moment diagrams. We're just going to find the reactions at this point. Let's call this point A and this point B, and then we'll try to we'll move on from there, integrating further to get our rotation and our deflection. So, to solve for our reactions, we're going to need to set up our equilibrium equations. So, we're going to have summation of force in the y direction. That's got to equal 0. That's going to equal negative 100 kips from this right there, plus the reaction at A in the y direction. That's got to sum to 0, so that's going to immediately just go ahead and give us AY is equal to positive 100 kips. As for the moment, let's take the moment about point A. That's going to be equal to, well, it's going to sum to 0, and that's going to be equal to the moment reaction at A. I'll call that AM, plus negative 100 kips times 10 feet gives us that the moment reaction at A has to be 1,000 kip feet counterclockwise. Okay, now we've got that. Let's determine our shear diagrams. Our shear is going to initially pop up to 100 kips because of the reaction we have at point A, and will remain at 100 kips for the full length of the beam, and then it will return to 0 because of this load right here. We're ending at 0. It's a free end. Looks good to me. Now let's do our moment. our moment is going to start at negative 1,000 kip feet. Keep in mind our sign convention, and it's going to linearly go up here. It's going to go up 1,000 kip feet linearly, because that's going to be, well, that's the area under our shear function. We end at 0. Good. To free end, it should have 0. So the functions represented by these are going to be that v, I'm going to say it's a function of x even though it's a constant, is 100 kips. Pretty easy function. Moment is the integral of the shear function. So it's the integral of 100 kips so it's 100 kip times x plus some constant integration c1. In this case, because we've got this reaction at point A, we can determine that c1 sure as heck better be negative 100 kip feet. So that's what we'll make our function. 100 kips times x minus 1,000 kip feet.